Welcome to week 3 of exploring the world of AI. Last week, we talked about how machines learn. This week is all about the bigger picture and to some extent also the smaller picture as well. So, all examples we've discussed so far have been cases in which the machine was doing a certain task pretty well. But what still remains an open question is, can machines think? Remember the most impressive AI we've spoken about in the beginning, something like the guys from the Transformers movies or the robot sidekicks from Star Wars. Something that is truly intelligent and able to think by itself. This kind of intelligent machine is actually something that is often referred to as strong AI. In contrast to the examples we saw last week, which you considered weak AI, we can distinguish two types of AI. Weak AI describes software that accomplishes a specific problem-solving or reasoning task. Examples for weak AI include playing the banana hunt game, playing chess, or detecting if an image shows a cat or a dog. While a weak AI system for image recognition will fail at playing chess, a strong AI might be good at a range of tasks and is not limited to a single application domain. Strong AI describes software that can perform the full range of cognitive tasks. So, while weak AI means that computers can be programmed to act and make us think they behave intelligently during a particular task at least, strong AI means that computers can be programmed so they really do think, just like we do. Let's use a mind experiment called the Chinese room to elaborate on strong AI. Imagine yourself standing in a room with an inbox to receive letters and an outbox to send letters to. You receive new messages containing questions in Chinese text via your inbox. As you're probably unable to speak Chinese, you'll have a hard time reading what's written in these messages. But what you have as a tool is a giant book where every question that you may receive is noted together with a correct answer. So, if you receive this combination of characters, you can just copy the then part of the matching rule in the book and put it into your outbox. In consequence, for a person standing outside of the room, you behave exactly as if you understood Chinese, while in fact you don't understand a single word of Chinese. What can we learn from this? How can we say something is truly intelligent or if there's just a rule for everything we asked? So, if there was a computer program that made the computer understand Chinese, this program could also be written down in the book of the Chinese room, since the Chinese room behaves similarly to how a computer is behaving, by simply using rules to match input and output. The main message of the Chinese room experiment is that intelligence cannot be broken down into computer instructions that can be automated. Machines can only be made to behave as if they were intelligent. Following this argument, there is no such thing as strong AI. But if the Chinese room works so well, how can we be sure that the person inside the room does not understand Chinese? Simply, we can't. For an observer, the room has demonstrated human-like intelligence, even though machines might not be able to think by themselves. Alan Turing, a pioneer of computer science and known, among other things, for cracking the Enigma code, developed the Turing test. The Turing test checks if a computer demonstrates intelligent behavior. In contrast to the Chinese room, the Turing test only tests for functionality, not for the presence of consciousness. So let's play a game called the imitation game. It is played with 3 people, a man, a woman, and a tester. The tester and the 2 people stay in different rooms, apart from each other. The tester does not know who is who. He just knows that in one room there is a man and in the other there is a woman. It's now his task to figure out in which room the woman is located. To find out in which the woman is, the tester is allowed to pose questions to both people. The communication between them happens via paper from a typewriter. Nowadays, we'd probably use a chat system for that. So it's now the man's objective to try and cause the tester to make wrong decisions. So, therefore, he's allowed to lie. The woman, on the other hand, actually wants to support the tester. When the tester might ask, will the person in the left room tell me the length of his or her hair? When the man is now supposed to answer, as his objective is to trying to fool the tester, he might answer something like, my hair is shingled and the longest strands are about 9 inches long. At least, he would have said that back in the 50s when Turing came up with the test. After asking a certain amount of questions, the tester has to decide in which of the rooms the woman and in which of the rooms the man is located. So now, what will happen if we replace the person in the left room of the game with a machine? Will the tester decide wrongly as often as when the game is played like this, as he does when the game is played between a man and a woman? This is the Turing test. Will a human tester that interacts not with a man and a woman, but with two players, one of them being a machine and one of them being a human, by exchanging written messages be able to determine which player is the computer? The argument is that if a computer is indistinguishable from a human in a general natural language conversation, then it must have reached human-level intelligence. The computer is considered intelligent if it cannot be distinguished from a human by observing its behavior, just like we observed with the Chinese room. Turing just excluded those conditions which make us immediately feel as if we were talking with a computer, such as the voice or the appearance, by using written communication. This way, the tester can't base his or her decision on superficial features. Also, we'll probably never have a strong AI. We might get computers that can trick us to such an extent as to pass the Turing test. Even though, according to the Chinese room argument, there is no presence of consciousness, the room or the machine can still behave or function as a conscious mind would. As we see, having a mind is not entirely about what is being computed. It's partly a matter of how something is being computed. And if you're computing things in a similar manner to the Chinese room by using this gigantic lookup table, it probably isn't intelligence. But if we're on the outside of the room, we might never know whether or not something has a mind. There is even a competition where computer programs compete to beat Turing's test. The Loebner Prize is an international contest where chatbots compete with each other to find the most human-like bot. This is an incredibly difficult challenge, as recreating human conversations is such a complex task, and instead of being an assistant or having a goal, human conversations covers a vast multitude of topics. A chatbot named Mitsuku won it 4 times in a row. So let's talk to her. I'm Stefan. What about you?
Hi, Stefan. I don't know whether or not I am Stefan. I am immortal and smarter than you.
What's your name?
My name is Mitsuku.
And what was my name again?
Once more, your name is Stefan.
From the above conversation, we can analyze that Mitsuku is keeping the previous chat context in mind while answering new questions. This is similar to what a human would do. But has it acquired intelligence? Let's see another chat. Let's ask her simple math questions that we might also ask a 10-year-old child. So John is 5 years old. Phil is 10 years older than him. How old is Phil?
Thanks for letting me know. Phil, 39.
Not quite. We see that she essentially answers each individual sentence on its own. So that's not quite what we wanted. So let's tell her.
Can you be more precise?
To fool us into thinking she is understanding us, she's then asking us questions, similar to what we might do when we did not listen carefully to someone. So, okay, now let's try to offend her. You're not overly clever, Mitsuko.
Well, why don't you teach me something instead of insulting me?
Here it is clearly demonstrated that the chatbot is far from acquiring human-level intelligence. It seems to not understand the context of the question and is trying to answer based on the words in the question. There are a number of examples showing the fact that chatbots cannot understand the context every time, but training them over a long time using day-to-day conversations can make them better in such tasks. Google recently proved this with a chatbot called Mina. As with our algorithms that are very good in classification or playing specific games, chatbots like Mitsuko are performing well in the tasks they are trained for, but they'll fail in something that they are not trained to. Unlike humans, they do not build logic in order to tackle a new problem. So, to answer a question from the beginning, can machines think? No, they'll most probably never be able to be intelligent as we humans are, but they already do a somewhat good job of pretending to be intelligent. Now it's time for you to chat with Mitsuko and make your own experiences. Find the respective task in the description. And that's it for today's lesson. Thanks for joining us. We'll see you tomorrow when we'll take a closer look at neural networks.